Imagine for a moment that you're sinking, not drowning. Nothing that dramatic or frightening, just gently descending through crystal clear water, like a feather falling through honey. The sunlight above gradually fades from brilliant blue to deep sapphire, then to an emerald twilight that seems to pulse with its own quiet rhythm. You continue down, and the water grows colder, pressing against you like an invisible embrace that tightens with every meter. The pressure builds slowly, steadily, until you realize you're entering a world so alien, so impossibly hostile to human life, that it might as well be another planet. And yet, here, in the deepest scar on Earth's surface, in darkness so complete that the very concept of light becomes meaningless, life thrives. Welcome to the Mariana Trench, a crescent-shaped gash in the Pacific Ocean floor that plunges nearly 11 kilometers below the waves, so deep that if you dropped Mount Everest into it, the peak would still be covered by over a mile of water. It's a place where the pressure is over 1,000 times greater than at sea level, where the weight of water above could crush a human body in milliseconds, where temperatures hover just above freezing, and where no ray of sunlight has ever penetrated. You might think such a place would be barren, sterile, empty, a watery graveyard at the bottom of the world, but you'd be wrong, beautifully, mysteriously, impossibly wrong. Perhaps you're listening to this while lying in bed, feeling the gentle weight of a blanket, the soft support of a pillow. Maybe you can hear the distant hum of traffic, or the whisper of wind through trees. These are the sounds and sensations of our world, the thin layer of habitability we call home. But tonight, we're going to sink deeper, much deeper, into a realm where the rules we know, the physics we trust, the very definition of what's possible for life, all begin to bend and blur like light through deep water. The Mariana Trench stretches across the floor of the Western Pacific, like a wound that won't heal, running for over 2,550 kilometers in a gentle arc east of the Philippines. It formed through a process so slow, so patient, that it makes human history look like a sneeze. The Pacific Plate, one of Earth's massive tectonic puzzle pieces, has been sliding beneath the Philippine Plate for millions of years, creating this profound depression in the ocean floor. But numbers and geological processes don't really capture what this place is. To understand the Mariana Trench, you have to understand water, not the friendly stuff that fills your bathtub or falls as rain, but water as a force, as weight, as an almost solid presence. Picture this: at sea level, the atmosphere presses on your body with about 14.7 pounds per square inch. You don't notice it because you've evolved to live with it, your body pushing back with equal force. Now, for every 10 meters you descend in the ocean, add another atmosphere of pressure. By the time you reach the deepest point in the Mariana Trench, a spot called Challenger Deep, you're under 1,086 bars of pressure. That's equivalent to having about 50 jumbo jets stacked on top of a person. At this pressure, the normal rules of chemistry start to shift. Gases compress, liquids behave strangely, proteins fold differently. The very molecules that make up living things begin to rebel against their usual configurations. Water itself becomes about 5% denser down there, squeezed by its own tremendous weight. The journey to Challenger Deep takes hours, even in the most advanced submersibles. As you descend, you pass through layers of the ocean, each with its own character, its own inhabitants, its own rules. The sunlight zone, or euphotic zone, extends down to about 200 meters. Here, photosynthesis still occurs, and the water dances with familiar life: fish that look like fish, jellyfish that pulse like living lace, dolphins that surface to breathe air just like we do. Below that lies the twilight zone, the mesopelagic, stretching down to about 1,000 meters. Here, the last whispers of sunlight fade to nothing, and bioluminescence becomes the dominant form of light. Creatures create their own stars in the darkness, flashing, glowing, signaling in a silent language of light that we're only beginning to understand. Deeper still is the midnight zone, the bathypelagic, reaching down to 4,000 meters. No sunlight has ever touched these waters. The pressure here would crush most surface life instantly. The temperature hovers just above freezing, and yet, life persists. Strange, wonderful, alien life that seems to mock our assumptions about what's necessary for survival. The abyssal zone comes next, stretching down to 6,000 meters. Here, the ocean floor spreads out in vast plains of sediment, accumulated over millions of years, from the constant snow of organic matter drifting down from above. It's a desert made of the dead, yet it supports its own ecosystem of scavengers and extremophiles. And finally, below everything else, lies the Hadal Zone, named after Hades, the Greek god of the underworld. This is the realm of the ocean trenches, the deepest places on our planet. The Mariana Trench is the deepest of them all, and Challenger Deep, at 10,994 meters below sea level, though measurements vary slightly, is the deepest point we know of in any ocean. The first confirmed journey to Challenger Deep happened on January 23, 1960. Two men, Jacques Piccard and Don Walsh, squeezed into a steel sphere attached to a huge flotation tank filled with gasoline, a vessel called the Trieste. The sphere was just barely big enough for two people to sit, surrounded by instruments and the curved steel walls that were all that stood between them and instant death. The descent took 4 hours and 47 minutes. As they sank, the Trieste groaned and creaked, its metal frame compressing under the increasing pressure. At 9,000 meters, a loud crack rang through the sphere. One of the outer windows had shattered, but the inner hull held, and they continued down. When they finally touched bottom, stirring up a cloud of fine sediment that had been undisturbed for perhaps millions of years, Piccard looked out through the tiny porthole and saw something that shouldn't have been there according to the science of the time. A fish, or at least something that looked like a fish, flat, about a foot long, moving slowly across the bottom. They only stayed for 20 minutes before beginning the 3-hour journey back to the surface. But those 20 minutes changed our understanding of life on Earth forever. That fish, or whatever Piccard saw, raised a question that scientists are still answering today. How does life exist under such crushing pressure? To understand this, we need to think about pressure at the molecular level. Most life on Earth's surface depends on proteins, complex molecules that fold into specific shapes to do their jobs. These shapes are held together by relatively weak chemical bonds that can be disrupted by changes in temperature, pH, or pressure. At the bottom of the Mariana Trench, the pressure should cause most proteins to denature, to unfold and become useless, like a paper origami crane crushed in a vise. But life in the deep has evolved remarkable solutions. Deep-sea organisms produce special molecules called piezolites from the Greek word piezine, meaning to press. These molecules, particularly one called trimethylamine oxide TMAO, act like molecular scaffolding, helping proteins maintain their shapes under pressure that would destroy surface life. The deeper a fish lives, the more TMAO it tends to have in its cells. It's like each creature carries its own internal pressure suit, built not from metal or ceramic, but from carefully balanced chemistry. Some scientists believe there's a depth limit, around 8,200 meters, where fish simply can't accumulate enough TMAO to survive. Below that, you need to be something else entirely. And what else is down there? The list reads like a catalog from an alien world. There are xenophyophores, single-celled organisms that can grow to be 10 centimeters across, making them giants in the world of single cells. They build elaborate shells from sediment particles, creating structures that look like delicate fans or spirals. How a single cell coordinates such construction remains a mystery. There are amphipods, small, shrimp-like creatures that have been found throughout the trench. Some of them are giants by amphipod standards, growing to over a foot long in a phenomenon called deep-sea gigantism. Nobody's entirely sure why some deep-sea creatures grow so large, but it might have to do with the cold temperatures slowing their metabolisms, allowing them to live longer and grow larger. In 2014, scientists discovered something even more surprising. At the deepest points of the Mariana Trench, in sediment samples from Challenger Deep, they found thriving communities of microbes. These organisms were not just surviving but actively feeding and reproducing at pressures that would liquefy a human being. Some of them were consuming organic matter that had drifted down from the surface. Others were performing chemosynthesis, creating energy from chemical reactions rather than sunlight. But here's where it gets truly strange. Some of these microbes were breaking down complex hydrocarbons, compounds that shouldn't naturally exist at such depths. Where were they coming from? The answer might lie in the trench itself. The Mariana Trench isn't just deep, it's geologically active. The same tectonic forces that created it continue to shape it, and along parts of the trench, scientists have discovered something remarkable. Hydrothermal vents and cold seeps, places where chemicals and minerals bubble up from the Earth's interior. These vents create oases of chemical energy in the nutritional desert of the deep ocean. Around them, entire ecosystems bloom in the darkness, based not on photosynthesis, but on chemosynthesis. Bacteria convert hydrogen sulfide and methane, chemicals that would be toxic to most surface life, into energy. These bacteria form the base of a food web that includes tube worms, clams, and other creatures that exist nowhere else on Earth. In 2012, filmmaker James Cameron made a solo descent to Challenger Deep in a specially designed submersible called the Deep Sea Challenger. Unlike Pickard and Walsh, who could only peer through a tiny porthole, Cameron brought high-definition cameras and powerful lights, illuminating this alien world for the first time in detail. What he found was not a barren moonscape but a living ecosystem. The seafloor was covered in what looked like a carpet of microbes, tinged green and gold in the submersible's lights. Amphipods scuttled through the sediment. Strange, translucent sea cucumbers drifted past like ghosts. The sediment itself seemed alive, releasing bubbles of gas, probably methane, that rose like inverse rain toward the surface far above. But perhaps the most surprising discovery came later. When scientists analyzed the samples Cameron brought back, they found that life in Challenger Deep was incredibly diverse. Over 200 different species of microorganisms were identified, many of them completely new to science. Some of these organisms had evolved unique ways to deal with the pressure, including modified cell membranes that remained fluid despite the crushing weight of water above. One particularly fascinating discovery was a type of bacteria that produces a compound called polyhydroxyalkanoate, a natural plastic. At the surface, some companies are trying to harvest similar bacteria to create biodegradable plastics. But in the Mariana Trench, these organisms have been quietly producing plastic-like compounds for millions of years, using them to store energy in an environment where food is scarce and meals are unpredictable. The food web in the Mariana Trench is unlike anything on the surface. With no sunlight, there's no photosynthesis, no plants, no algae. Instead, the entire ecosystem depends on marine snow, a constant drift of organic matter falling from above. Dead plankton, fecal pellets, molted shells, and other detritus sink slowly through the water column, taking weeks or even months to reach the bottom. By the time this marine snow reaches the Haddle zone, most of the easily digestible nutrients have been consumed by creatures in the waters above. What arrives at the bottom is the equivalent of metabolic table scraps, tough, nutrient-poor material that requires specialized enzymes to break down. The organisms of the deep have evolved to be incredibly efficient at extracting energy from this meager rain of death. But marine snow isn't the only source of food in the deep. Occasionally, a windfall arrives in the form of a whale fall, the carcass of a dead whale that sinks to the ocean floor. A single whale carcass can support a complex ecosystem for decades. First come the hagfish and sleeper sharks, tearing away the soft tissue. Then polychaetae worms and crustaceans move in, cleaning the bones. Finally, bacteria break down the lipids trapped in the bones, releasing sulfides that support chemosynthetic organisms for years. Scientists have found evidence of whale falls in the Mariana Trench, including bones that have been colonized by unique species found nowhere else. It's possible that these whale fall communities act as stepping stones, allowing species to disperse across the vast distances of the deep ocean floor. The creatures of the Mariana Trench have evolved remarkable adaptations beyond just pressure resistance. Many of them are transparent or translucent, an adaptation that makes them nearly invisible in the darkness. Others are bright red, a color that appears black in the deep ocean because red light is the first to be absorbed by water. Some have developed enlarged eyes to capture what little light exists from bioluminescence. Others have lost their eyes entirely, navigating instead through chemical senses, detecting the faintest traces of food or mates in the water. The snailfish, one of the few fish species found in the deepest parts of the trench, has a body that's essentially held together by a gelatinous substance, with bones so soft they're almost cartilaginous, adaptations that help it survive the pressure. But pressure isn't the only challenge. The temperature at the bottom of the Mariana Trench hovers around 1-4 degrees Celsius, just above freezing. Many deep-sea organisms have evolved antifreeze proteins to prevent ice crystals from forming in their cells. Their metabolisms have slowed to a crawl, allowing them to survive on minimal food. Some deep-sea creatures can go months or even years between meals. The isolation of the Mariana Trench has led to remarkable examples of evolution in action. Many species found there exist nowhere else on Earth. They've been evolving in isolation for millions of years, adapting to conditions that would instantly kill their surface-dwelling relatives. It's evolution's own laboratory, a place where life has been forced to find new solutions to problems that don't exist anywhere else on our planet. Recent discoveries have only added to the mystery. In 2020, scientists discovered a new species of bacteria in the Mariana Trench that feeds on oil. Not oil from human pollution, but natural oil compounds that seep from the Earth's crust. These bacteria could potentially help us clean up oil spills, turning an organism from the most extreme environment on Earth into a tool for environmental protection. Even more remarkably, scientists have found that some organisms in the Mariana Trench contain chemicals with potential medical applications. Deep-sea bacteria produce unique antibiotics to compete with other microbes for resources. Some of these compounds show promise in fighting drug-resistant infections. Others might lead to new treatments for cancer or neurological diseases. But perhaps the most unsettling discovery in the Mariana Trench wasn't a new species or a novel compound. It was something terrifyingly familiar. Plastic. In 2019, American explorer Victor Vescovo made multiple dives to Challenger Deep and found something that shouldn't have been there. A plastic bag, at nearly 11 kilometers below the surface, in what should be one of the most pristine environments on Earth. Human pollution had already arrived. This wasn't an isolated incident. Researchers have found microplastics in amphipods from the Mariana Trench. These tiny creatures, living in the deepest ocean, have plastic fibers in their guts. Some of these plastics contain pollutants that were banned decades ago, suggesting they've been cycling through the ocean for generations before finally settling in the deepest place on Earth. It's a sobering reminder that nowhere on our planet is truly untouched by human activity. The rain of marine snow that feeds the deep ocean now includes a steady drift of microplastics. The same adaptations that allow deep-sea creatures to efficiently extract nutrients from scarce food sources also cause them to accumulate toxins and plastics. Yet life in the Mariana Trench continues, adapting even to this new challenge. Some bacteria have been found that can actually break down certain types of plastic, though the process is slow and the byproducts aren't always harmless. It's evolution in real time, organisms adapting to a pollutant that didn't exist until humans created it less than a century ago. The study of life in the Mariana Trench has implications beyond our own planet. Astrobiologists, scientists who study the possibility of life elsewhere in the universe, are particularly interested in these extreme environments. If life can exist under 1,000 atmospheres of pressure, in complete darkness, at near freezing temperatures, feeding on chemicals that would be toxic to most organisms, then perhaps life could exist in the subsurface oceans of Jupiter's moon Europa or Saturn's moon Enceladus. The organisms of the Mariana Trench have expanded our definition of what's habitable. They've shown us that life doesn't need sunlight, doesn't need moderate pressures, doesn't need what we traditionally think of as food. It just needs energy, in whatever form it can get it, and the chemical building blocks to construct itself. This has led some scientists to propose that the deep ocean might have been where life on Earth first began. Deep-sea hydrothermal vents provide a steady source of chemical energy, protection from the harsh radiation that bombarded early Earth's surface, and a rich mix of minerals and compounds. The pressure that seems so hostile to us might have actually helped early organic molecules come together, forced into close proximity by the weight of water above. As we slowly ascend from the depths of the Mariana Trench, rising through the layers of pressure and darkness back toward the familiar world of air and sunlight, it's worth pausing to consider what this place means. The Mariana Trench is Earth's final frontier, a place less explored than the surface of the moon. We've sent 12 people to walk on the lunar surface, but only a handful have descended to Challenger Deep. We have better maps of Mars than we do of our own ocean floor. In many ways, the deep ocean is more alien to us than outer space. Yet this alien world is part of our own planet, connected to us through the global circulation of water, nutrients, and even pollutants. The organisms living in the deepest places on Earth are our distant relatives, sharing the same basic biochemistry, the same genetic code, the same fundamental spark of life that animates everything from bacteria to blue whales. The Mariana Trench reminds us that life is more creative, more persistent, more adaptable than we often give it credit for. Every time we think we've found the limits of life, we discover organisms pushing beyond those boundaries. Too hot? There's life in boiling water. Too cold? There's life in Antarctic ice. Too acidic? Too alkaline? Too salty? Too radioactive? Life finds a way. Perhaps that's the most comforting message from the deep. In a universe that often seems hostile to life, in a cosmic void where we've yet to find any other living world, the Mariana Trench tells us that life is tougher than it looks. It bends but doesn't break. It adapts, persists, and even thrives in conditions that seem impossible. Tonight, as you drift off to sleep under the gentle pressure of one atmosphere, in temperatures that would seem scorching to a deep-sea creature, breathing air that would be useless to the chemosynthetic bacteria of the deep, remember that you're connected to those alien organisms 11 kilometers below the Pacific. You share this planet with creatures that have never seen sunlight, that live under pressure, that would crush you instantly, that feed on chemicals you couldn't digest, and yet, you and they are part of the same story, the story of life on Earth, finding its way into every possible niche, adapting to every challenge, persisting against all odds. The Mariana Trench isn't just a deep hole in the ocean floor, it's a testament to life's ingenuity, a laboratory of evolution, a reminder of how much we still don't know about our own planet. It's a place where the rules we take for granted don't apply, where life has rewritten its own playbook, where the impossible becomes routine. And perhaps most remarkably, it's a place that's still revealing its secrets. Every expedition brings back new species, new behaviors, new chemistry that we didn't know existed. The deepest place on Earth continues to surprise us, to challenge our assumptions, to expand our understanding of what's possible. So rest easy tonight, knowing that far below the waves, in the eternal darkness of Earth's deepest scar, life continues its patient work, building, feeding, reproducing, evolving. The creatures of the Mariana Trench don't know or care that they live in the most extreme environment on our planet. To them, it's simply home, and in that simple fact lies perhaps the deepest truth of all. Life doesn't need our permission to exist. It doesn't need ideal conditions or comfortable circumstances. It just needs a chance, however slim, however challenging. And given that chance, life finds a way to transform even the deepest, darkest, most pressure-filled places into something remarkable. A living world at the bottom of the world, thriving in the beautiful darkness, proving once again that our planet still has mysteries to share, wonders to reveal, and stories to tell. Sweet dreams. And remember, even at the bottom of the deepest ocean, in the coldest, darkest, most impossible places, life whispers on. But wait, there's something even stranger happening in the Mariana Trench that we haven't talked about yet. Something that challenges our very understanding of water itself. You see, water at the bottom of the Mariana Trench isn't quite the same substance you drink from your glass or swim through at the beach. Under such extreme pressure, water molecules are forced closer together than they would ever naturally occur at the surface. The hydrogen bonds that give water its unique properties, its ability to dissolve substances, its surface tension, its role as the universal solvent, all of these begin to change. At pressures exceeding 1,000 atmospheres, water becomes about 5% denser than at the surface. That might not sound like much, but it's enough to alter the fundamental chemistry of life. Reactions that would happen quickly at the surface, slow to a crawl, molecules that would normally dissolve refuse to break apart. Even the pH of water shifts slightly, becoming more acidic under pressure. This altered water creates unique challenges for the organisms living in it. Their cell membranes, which need to be fluid to function properly, tend to solidify under pressure. Imagine butter hardening in a refrigerator. To combat this, deep-sea organisms incorporate more unsaturated fats into their membranes, keeping them fluid even under crushing pressure. Some species have membranes that are 80% unsaturated fats, compared to about 30% in surface fish. But here's where it gets truly fascinating. Some scientists believe this pressure-altered water might actually preserve organic molecules better than surface water. The same pressure that makes life difficult also slows down the processes of decay. DNA, proteins, and other biological molecules might survive longer in the deep than anywhere else on Earth. The Mariana Trench could be a kind of molecular time capsule, preserving chemical evidence of ancient life. For decades, scientists believed the deep ocean was a silent world. After all, without air-filled swim bladders to vibrate, how could fish make sounds? Without vocal cords, how could anything communicate? The pressure would surely muffle any noise, creating a world of perpetual quiet. But they were wrong, magnificently, mysteriously wrong. When researchers first lowered sensitive hydrophones into the Mariana Trench, they expected to hear nothing but the occasional creak of their own equipment. Instead, they discovered a hidden soundscape: clicks, whistles, rumbles, and rhythmic pulses that suggested a bustling acoustic community. Some of these sounds come from the Earth itself. The Mariana Trench sits along the Pacific Ring of Fire, where tectonic plates grind against each other. Deep-sea earthquakes send low-frequency rumbles through the water. Underwater landslides create thunderous roars that can travel thousands of kilometers. Volcanic activity produces its own unique acoustic signature, a combination of explosions, gas releases, and the crack of cooling lava meeting cold water. But mixed in with these geological sounds are biological ones. In 2016, researchers recorded a mysterious sound they nicknamed the Western Pacific biotwang, a complex call lasting about 3.5 seconds, starting at around 38 Hz and gliding up to 8,000 Hz. It sounded almost metallic, like a science fiction spacecraft. After months of analysis, they concluded it was probably a new type of baleen whale call, possibly from a minke whale. But the fact that such a distinctive sound had never been recorded before shows how little we know about deep-sea acoustics. Even more intriguing are the sounds that remain unexplained. The deep ocean is full of acoustic mysteries, repeating patterns that suggest communication, but from unknown sources. Some scientists speculate that deep-sea creatures might use sound in ways we haven't imagined. Perhaps the pressure actually helps sound travel more efficiently. Perhaps creatures we thought were silent have been singing all along, just at frequencies or patterns we didn't know how to detect. The amphipods of the Mariana Trench, those shrimp-like creatures that thrive at the deepest depths, have been observed making clicking sounds by snapping their claws. But the purpose remains unclear. Are they communicating, echolocating in the darkness, stunning prey? We simply don't know. Speaking of darkness, let's talk about one of the most beautiful paradoxes of the deep ocean. It's a place of absolute darkness that's actually full of light. Bioluminescence. The ability of living organisms to produce light is so common in the deep sea that it's actually the rule rather than the exception. Scientists estimate that 90% of organisms below 500 meters can produce their own light. In the Mariana Trench, where no sunlight has ever penetrated, life has created its own constellation of living stars. But this isn't the gentle, romantic glow of fireflies on a summer evening. Deep-sea bioluminescence is a serious survival tool, used for hunting, defense, communication, and finding mates in the eternal darkness. The light comes from chemical reactions, typically involving a compound called luciferin and an enzyme called luciferin. When these combine with oxygen, they produce light without heat, a cold fire that burns in the darkness. Some creatures use bioluminescence as a lure. Deep-sea anglerfish dangle glowing appendages in front of their mouths, attracting curious prey directly into their jaws. Others use it for defense. When threatened, some deep-sea jellies release glowing clouds of luminescent chemicals, creating a bright distraction while they escape into the darkness. Perhaps the most clever use is what scientists call the burglar alarm strategy. When a small creature is grabbed by a predator, it lights up brilliantly, essentially screaming, "Look at me," in light. This attracts even larger predators, which might attack the original attacker, giving the small creature a chance to escape in the chaos. In the Mariana Trench, researchers have observed creatures using bioluminescence in ways that seem almost artistic. Siphonophores, colonial organisms related to jellyfish, create elaborate light displays, pulsing in patterns that ripple along their bodies like living neon signs. Some can be over 40 meters long, making them among the longest animals on Earth, creating light shows that stretch through the darkness, like deep-sea aurora. But here's something that will truly bend your mind. Some creatures in the deep use red bioluminescence. Remember how I mentioned that red light is absorbed quickly by water? Most deep-sea creatures have evolved eyes that can't see red at all. There's no point when red light never reaches the deep. But a few clever predators, like the stoplight loosejaw fish, produce their own red light. They essentially have private headlights that their prey can't see, hunting with invisible beams in a world already devoid of light. In the Mariana Trench, even time seems to flow differently. Not in any relativistic sense. We're not talking about Einstein's theories here, but in a biological sense that's equally profound. Life in the deep moves slowly. The cold temperatures slow metabolisms to a crawl. Some deep-sea clams are estimated to be over 100 years old, possibly much older. They grow so slowly that their shells record centuries of ocean history in their growth rings, like trees of the deep. Deep-sea sharks, like the Greenland shark which occasionally ventures into deep trenches, might live for 400 years or more. They reach sexual maturity at around 150 years old, an age when most species would have been dead for over a century. They swim slowly, hunt slowly, digest slowly. In the deep, there's no rush. Energy is too precious to waste on haste. This slow pace of life has profound implications for evolution. Generations turn over so slowly that evolutionary changes take longer to manifest. Yet paradoxically, the extreme environment also drives rapid adaptation when changes do occur. It's evolution in slow motion and fast forward simultaneously. The reproductive strategies of deep-sea creatures reflect this different relationship with time. Many species produce very few offspring, but invest heavily in each one. Some deep-sea octopuses brood their eggs for over 4 years, the longest brooding period known for any animal. The mother doesn't eat during this entire time, slowly starving as she protects her developing young. It's a strategy that seems impossibly costly, but in the stable, slow-moving world of the deep, it works. The sediment at the bottom of the Mariana Trench is more than just mud. It's a library. Each layer represents a different time period, preserving a record of ocean conditions, climate, and life going back millions of years. Scientists call these sediment cores natural archives, and they're revolutionizing our understanding of Earth's history. When researchers extract sediment cores from the Mariana Trench, they're pulling up compressed time. A single meter of sediment might represent 100,000 years of accumulation. The layers alternate between light and dark, recording changes in ocean productivity, volcanic eruptions, even asteroid impacts. Microscopic shells of plankton preserve information about ancient ocean temperatures and chemistry. But the sediment holds more than just geological information. It contains environmental DNA, genetic material shed by organisms that lived in or above the trench. By analyzing this DNA, scientists can identify species that lived millions of years ago, reconstructing ancient ecosystems from genetic fragments preserved in the mud. Recently, researchers discovered that sediments in the Mariana Trench contain unusually high levels of carbon-14, a radioactive isotope created by nuclear bomb tests in the 1950s and 60s. This human signature has already been incorporated into the geological record of the deepest place on Earth. Future scientists, millions of years from now, will be able to identify our nuclear age in the sediment layers of the Mariana Trench. Every journey to the Mariana Trench is a leap into the unknown, a billion-dollar gamble against pressure, technology, and time. Let me tell you about some of the expeditions that didn't make headlines but changed our understanding of the deep. In 2009, the unmanned vehicle Nereus reached Challenger Deep, spending over 10 hours on the bottom. Unlike previous expeditions that could only observe, Nereus could manipulate objects, collecting samples with a robotic arm. On one dive, it discovered something unexpected: rocks covered in what looked like fur. Closer inspection revealed these were bacterial mats, so thick they resembled carpet, thriving on chemicals seeping from the rocks. But Nereus met a tragic end. In 2014, while exploring the Kermadec Trench, the second deepest trench on Earth, it imploded under pressure at 9,990 meters depth. The loss was devastating, not just financially, but scientifically. Nereus had been one of only a handful of vehicles capable of reaching full ocean depth. Its destruction reminded everyone that despite our technology, the deep ocean doesn't forgive mistakes. The Chinese have also been exploring the Mariana Trench with their submersible Fenduji, which means striver. In 2020, it set a new national record by diving to 10,909 meters with 3 people aboard. During their dives, they discovered forests of sea anemones in places where scientists didn't think such complex organisms could survive. These anemones, some over a meter tall, swayed in currents that shouldn't exist at such depth, feeding on particles too small to see. But perhaps the most poetic expedition was one that almost no one knows about. In 2018, a small team of researchers sent down time capsules to various depths in the Mariana Trench. These capsules contained messages, photographs, and DNA samples from people around the world. The idea was to preserve a snapshot of humanity in the most protected place on Earth. The capsules are designed to last 10,000 years, waiting in the darkness for future generations, or perhaps future species, to discover. We need to talk more about pollution in the Mariana Trench, because it's more extensive and more troubling than just plastic bags and microfibers. Researchers have found that amphipods from the Mariana Trench contain levels of industrial pollutants called PCBs, polychlorinated biphenyls, that are 50 times higher than crabs from one of China's most polluted rivers. These chemicals were banned in the 1970s, but they're still circulating through ocean systems, concentrating in the bodies of deep-sea creatures through a process called bioaccumulation. The discovery was shocking, because scientists had assumed the deep trenches were isolated from surface pollution, but it turns out that the Mariana Trench acts like a sink for pollutants. Particles carrying industrial chemicals sink into the trench and can't escape. The same topography that makes the trench unique also makes it a trap for humanity's waste. Even more disturbing, radioactive carbon from nuclear bomb tests has been found in the muscle tissues of amphipods from the Mariana Trench. These creatures, living in the most remote ecosystem on Earth, carry the atomic signature of human warfare in their bodies. They're swimming monuments to the Anthropocene, the proposed geological epoch defined by human impact on Earth. But here's the paradox: The same expedition that discovered this pollution also found that the Mariana Trench might help us solve our pollution problems. Bacteria, isolated from the trench, can break down oil and other hydrocarbons at pressures that would kill normal oil-eating bacteria. Some produce enzymes that can decompose plastics. Others can neutralize toxic chemicals. One particularly promising discovery is a bacterium that produces a compound called tetrodotoxin, the same poison found in pufferfish. But this bacterium has been found to break down synthetic chemicals that nothing else can touch. Scientists are now trying to understand how it does this, hoping to engineer similar capabilities in other organisms. The organisms of the Mariana Trench might hold keys to some of humanity's biggest challenges, and not just pollution. Let me share some of the most extraordinary discoveries that are emerging from the deep. In 2017, scientists discovered that some bacteria from the Mariana Trench produce compounds that kill cancer cells. These compounds work differently from existing chemotherapy drugs, targeting cancer cells through mechanisms we don't fully understand. One compound, now in early clinical trials, appears to be particularly effective against pancreatic cancer, one of the deadliest forms of the disease. Another discovery: some deep-sea bacteria produce natural sunscreens. Living in eternal darkness, you might wonder why they need protection from UV radiation. The answer lies in their evolutionary history. These bacteria likely evolved near the surface billions of years ago, when Earth's atmosphere provided less UV protection. They've retained the ability to produce these protective compounds even after millions of years in the darkness. These compounds are now being studied as potential next-generation sunscreens that are both more effective and more environmentally friendly than current options. The pressure-resistant proteins found in deep-sea organisms are revolutionizing biotechnology. Enzymes from Mariana Trench bacteria remain stable and active at pressures that would destroy normal proteins. This has huge implications for industrial processes that require high pressure. One company is already using deep-sea enzymes to improve the production of biofuels, making the process more efficient and less energy-intensive. Perhaps most remarkably, studies of how deep-sea organisms survive crushing pressure are informing new approaches to treating traumatic brain injuries. When the brain swells after injury, increased pressure can damage neural tissue. By understanding how deep-sea creatures protect their neural tissue from pressure, researchers are developing new treatments that could save lives and prevent permanent brain damage. The Mariana Trench isn't just biologically active, it's geologically alive in ways we're only beginning to understand. The subduction zone, where the Pacific Plate dives beneath the Philippine Plate, is one of the most dynamic places on Earth, and it's teaching us about processes that shape our entire planet. Recent discoveries have revealed that the Mariana Trench is recycling Earth's crust in unexpected ways. As the Pacific Plate descends, it carries with it millions of years of accumulated sediment, including the remains of countless marine organisms. This organic material is subjected to incredible heat and pressure as it's pushed deeper into Earth's mantle. Some of it melts and returns to the surface through volcanic eruptions. The rest is incorporated into Earth's interior, potentially affecting the chemistry of the entire planet. But here's what's truly mind-blowing. Water is being carried into Earth's interior at rates far higher than scientists previously thought. The descending plate acts like a conveyor belt, transporting ocean water deep into the mantle. Researchers now estimate that the Mariana Trench alone transports 4 times more water into Earth's interior than previously calculated. This has profound implications for understanding Earth's water cycle, volcanic activity, and even the long-term stability of our oceans. The trench is also revealing secrets about earthquakes. The deep earthquakes that occur in subduction zones like the Mariana Trench shouldn't be possible according to traditional theories. At depths greater than 70 kilometers, rocks should be too hot and ductile to break suddenly. Yet earthquakes occur at depths of over 600 kilometers beneath the Mariana Trench. These deep earthquakes might be caused by phase transitions, sudden changes in mineral structure under pressure, rather than traditional rock fracturing. Understanding these deep earthquakes could help us predict and prepare for seismic events that affect millions of people living along subduction zones. In 2018, scientists detected the largest deep earthquake ever recorded near the Mariana Trench, a magnitude 8.2 event at a depth of 600 kilometers. Despite its power, it caused little surface damage because of its depth, but it sent seismic waves through the entire planet, making the Earth ring like a bell for days. These waves provided unprecedented data about Earth's internal structure, revealing previously unknown features in the mantle. The extremophiles of the Mariana Trench, organisms that thrive in conditions that would kill most life, are rewriting our understanding of evolution and the limits of biology. These creatures haven't just adapted to extreme conditions, they require them. Bring them to the surface, to our comfortable world of moderate pressure and temperature, and they die almost instantly. Consider the barophilic bacteria, organisms that not only tolerate high pressure, but need it to survive. Some species from the Mariana Trench can't grow at pressures below 400 atmospheres. Their entire biochemistry is tuned to high pressure. Their enzymes only fold correctly under pressure. Their DNA replication machinery only works when squeezed by the weight of 7 miles of water. This has led scientists to a profound realization. Life doesn't just adapt to extreme environments, it can become addicted to them. The extremophiles of the Mariana Trench are so specialized that they've passed a point of no return. They can never return to the surface world their ancestors came from. They're permanently exiled to the deep, bound to their extreme environment by their own evolutionary success. But this specialization has given them remarkable abilities. Some produce antifreeze proteins more effective than anything we can synthesize. Others have DNA repair mechanisms that could revolutionize cancer treatment. One species of bacteria can survive radiation doses 1,000 times higher than would kill a human, not because it lives near radioactive vents, but because the same mechanisms that protect it from pressure damage also protect against radiation. The study of these organisms is also changing our understanding of how life began on Earth. Many scientists now believe that life might have originated in deep-sea environments similar to the trenches. The pressure could have helped organic molecules come together. The chemical energy from hydrothermal vents could have powered the first metabolisms. The isolation could have protected fragile early life from the harsh conditions on Earth's early surface. What does the future hold for the Mariana Trench? The answer is both exciting and troubling. On the positive side, technology is finally catching up to our curiosity. New submersibles are being built that can stay at depth for days rather than hours. Advanced sensors can detect chemicals at concentrations of parts per trillion. DNA sequencing technology allows us to identify organisms from just fragments of genetic material. We're on the verge of a golden age of deep-sea exploration. China, Japan, and the United States are all developing new deep-sea research programs. Private companies are getting involved too. Some are interested in deep-sea mining. The Mariana Trench and other deep-sea areas contain valuable minerals like manganese, cobalt, and rare earth elements. Others are bioprospecting, searching for organisms with commercially valuable properties. But this increased interest brings dangers. Deep-sea mining could destroy ecosystems we barely understand. The noise from mining operations could disrupt the acoustic environment that deep-sea creatures depend on. The sediment plumes from mining could smother life across vast areas. There's also the continuing problem of pollution. As surface waters become more polluted, more contaminants will eventually reach the deep. Climate change is altering ocean chemistry, making the water more acidic. This acidification is already affecting the shells and skeletons of deep-sea organisms. Temperature changes at the surface are altering the patterns of marine snow that feed the deep ecosystem. Yet there's hope. The Mariana Trench was designated a U.S. National Monument in 2009, providing some protection. International agreements are being negotiated to regulate deep-sea mining. Scientists are working to establish baseline data about deep-sea ecosystems before they're disturbed. The Mariana Trench forces us to confront fundamental questions about our place in the world. Here we have an environment on our own planet that's more alien than anything we're likely to find on Mars. It's a place where the rules we take for granted don't apply, where life has found solutions we never imagined possible. The trench reminds us that Earth is not just our planet, it's home to countless forms of life, most of which exist in places we'll never see, living lives we can barely comprehend. The organisms of the deep don't care about us, don't know we exist, and would continue their ancient patterns whether humanity thrives or disappears. There's something humbling about that. We often think of ourselves as the dominant species on Earth, but we're really just surface dwellers, clinging to the thin skin of a planet whose depths we've barely explored. The real rulers of Earth might be the microbes of the deep, outnumbering us by trillions, outlasting us by billions of years, thriving in places we can only visit with million-dollar machines. Yet there's also something inspiring about our relationship with the deep, that we, air-breathing mammals who evolved on African savannas, have found ways to explore the deepest parts of the ocean, speaks to the power of curiosity and ingenuity. Every journey to the Mariana Trench is a testament to human creativity and courage. The research happening in the Mariana Trench is changing how we do science itself. Traditional scientific disciplines, biology, chemistry, geology, physics, blur and merge in the deep. You can't understand the organisms without understanding the chemistry. You can't understand the chemistry without understanding the geology. Everything is connected in ways that force scientists to think beyond their specialties. This interdisciplinary approach is creating new fields of study. Geomicrobiology explores how microbes influence geological processes. Astrobiology uses deep-sea environments as analogs for alien worlds. Biomimetics seeks to copy the innovations of deep-sea life for human technology. The data coming from the Mariana Trench is also overwhelming traditional analysis methods. A single expedition can generate terabytes of video, thousands of samples, millions of data points. Artificial intelligence and machine learning are being deployed to help make sense of it all. Algorithms are being trained to identify new species from video footage, to predict where valuable organisms might be found, to model how deep-sea ecosystems might respond to change. Let me share some stories from researchers who've worked with specimens from the Mariana Trench, stories that rarely make it into scientific papers, but reveal the human side of deep-sea science. Dr. Patricia Fryer, who has studied the Mariana Trench for over 30 years, tells of the first time she saw living bacteria from Challenger Deep under a microscope. They were moving, slowly but definitely moving, under pressure that should have crushed them. She said she actually cried, overwhelmed by seeing life from Earth's most extreme environment thriving in a petri dish. A Japanese researcher, who asked to remain anonymous, spent 3 years trying to culture a particular bacterium from the Mariana Trench. It would only grow under exact pressure, temperature, and chemical conditions. One night, exhausted after another failed attempt, he accidentally knocked over a container of the growth medium. As he cleaned it up, he noticed something. Where the medium had spilled and mixed with seawater from another experiment, the bacteria were thriving. The accident revealed that the bacteria needed a trace mineral present in that particular seawater sample, a discovery that led to breakthrough in understanding deep-sea microbiology. Then there's the story of the singing amphipod. A researcher was reviewing audio recordings from the Mariana Trench when she noticed a pattern, a series of clicks that repeated every 2.3 seconds, lasting for hours. She spent months analyzing the sound, convinced it was biological. Finally, she realized it was coming from a small amphipod repeatedly striking its claw against the hydrophone, possibly attracted to its electromagnetic field. But the regularity of the pattern still puzzles scientists. Was it communication, territoriality, or just an arthropod with impeccable timing? The Mariana Trench isn't just deep in space, it's deep in time. The water at the bottom of the trench has been isolated from the surface for over 1,000 years. It's older than most nations, older than most languages, older than most of human history. This ancient water carries chemical signatures from a different Earth. It has different isotope ratios, different dissolved gas concentrations, different trace elements. It's a liquid time capsule, preserving information about ocean conditions from before the Industrial Revolution, before the Renaissance, before the Norman conquest of England. Scientists are now using this ancient water to understand how the ocean has changed over time. By comparing deep trench water with surface water, they can track how human activities have altered ocean chemistry. The results are sobering. Even the deepest, most isolated water on Earth shows signs of human impact. But this ancient water also holds secrets about natural climate cycles. The ratios of different oxygen isotopes in the water reveal information about past ice ages. The concentration of dissolved gases tells us about ancient atmospheric conditions. The trace metals record volcanic eruptions and asteroid impacts from centuries past. As we near the end of our journey into the Mariana Trench, it's worth considering what this place represents for humanity's future. Some visionaries see the deep ocean as humanity's next frontier for colonization. They imagine pressure-resistant habitats on the seafloor, mining operations, extracting resources, underwater cities powered by hydrothermal energy. It's a vision that seems like science fiction, but so did space stations and moon landings once upon a time. Others see the deep ocean as a library we must preserve, not exploit. They argue that the organisms of the Mariana Trench and other deep-sea environments hold solutions to problems we haven't even identified yet. Destroying these ecosystems for short-term gain would be like burning a library of books in languages we haven't learned to read. There's also the perspective that the deep ocean should remain wild, one of the last places on Earth where nature exists without human interference. In an increasingly managed and modified world, perhaps we need places like the Mariana Trench to remain untouched, reminders of a planet that existed before us and will exist after us. And so, dear listener, we come to the end of our descent into Earth's deepest place. We've journeyed through crushing pressure and eternal darkness, past creatures that glow with their own light, and bacteria that eat rocks, through water older than kingdoms and sediments that record the history of the world. But perhaps the most profound discovery isn't in the Mariana Trench itself, it's in what the trench reveals about us. That we, fragile beings who need air to breathe and warmth to survive, have found ways to explore Earth's most hostile environment, that we've developed the technology, the knowledge, and the courage to descend to places our bodies could never go. The Mariana Trench reminds us that Earth still holds mysteries, that there are still frontiers to explore, still questions to answer. In an age where it can feel like everything has been discovered, mapped, and cataloged, the deep ocean whispers, not yet, not even close. Every creature living in the Mariana Trench is a testament to life's creativity, resilience, and determination. They've found ways to turn the impossible into the routine, the lethal into the livable. They've shown us that life doesn't need our permission or our understanding to thrive. As you drift off to sleep tonight, perhaps you'll dream of sinking slowly through dark water, past glowing jellies and translucent fish, down to where the pressure would crush you in an instant, but where life has found a way to flourish. Perhaps you'll imagine the ancient water, older than memory, carrying its chemical stories through the darkness. Perhaps you'll think of the scientists and explorers who risk everything to bring back knowledge from the deep. Or perhaps you'll simply rest easier knowing that our planet still holds wonders, that there are still places where the impossible happens every day, where life pushes the boundaries of what we thought possible. The Mariana Trench is more than just a deep hole in the ocean. It's a reminder that Earth is stranger, more wonderful, and more resilient than we often give it credit for. It's proof that life finds a way, always and everywhere, even in the deepest, darkest, most pressure-filled places imaginable. Sweet dreams, and remember, 11 kilometers below the Pacific waves, in pressure that would crush you instantly, in darkness that has never known sunlight, life continues its ancient dance, proving once again that our planet's greatest stories are still being written in places we've barely begun to read. The deep calls to the deep, And sometimes, if we're brave enough and curious enough, we answer. Let's talk about the extraordinary machines that make exploring the Mariana Trench possible, because getting to the bottom of the ocean is arguably harder than getting to space. When you send a rocket to space, you're dealing with 1 atmosphere of pressure difference. When you send a submersible to Challenger Deep, you're dealing with over 1,000 atmospheres. In space, if your vessel springs a leak, air slowly escapes. In the deep ocean, if your vessel springs a leak, water shoots in with the force of a bullet, and the entire structure can implode in milliseconds. The Trieste, that pioneering bathyscaphe from 1960, was essentially a giant gasoline balloon with a steel sphere attached. The gasoline, being lighter than water and incompressible, provided buoyancy. The steel sphere, just 2 meters in diameter with walls 12.7 centimeters thick, protected its occupants. The sphere was so heavy, it had to be precisely calculated. Too heavy, and it would sink forever. Too light, and it couldn't descend. But here's a detail that still amazes engineers. The viewing window on the Trieste was made of a single piece of conical plexiglass, designed by the same company that made windows for spacecraft. Under pressure, this cone would actually compress and deform, but in a predictable way that maintained its integrity. It was a window that got stronger the deeper it went, up to a point. Modern submersibles are marvels of engineering that would seem like magic to the Trieste's designers. James Cameron's deep-sea Challenger was built like a vertical torpedo, designed to fall quickly to the bottom and rise quickly back up. Its pressure sphere was made from a special steel alloy that took years to develop. The sphere was machined to tolerances of less than a millimeter. Any imperfection could create a weak point that would fail catastrophically under pressure. The newest generation of deep-sea vehicles uses syntactic foam, a material made of tiny glass spheres embedded in epoxy resin. Each sphere is hollow, providing buoyancy, but so small that if one fails, it doesn't affect the others. This foam can withstand tremendous pressure while remaining lighter than water. It's like having millions of tiny submarines working together to keep the vehicle afloat. But perhaps the most impressive technology is the manipulator arms these vehicles carry. Imagine trying to pick up a delicate specimen with a robotic arm while sitting in a sphere being squeezed by the weight of Mount Everest. The hydraulic systems have to work at pressures that would explode normal equipment. The joints have to move smoothly, despite the crushing force trying to freeze them in place. And the operators have to control these arms with millimeter precision while looking through tiny portholes or video screens. The cameras and lights on these vehicles are engineering miracles in their own right. LED lights that can illuminate the darkness without generating heat that would crack the pressure housings. Cameras that can capture 4K video through pressure housings that distort the image. Lasers that can measure distances and sizes in an environment where normal reference points don't exist. Scientists studying the Mariana Trench have had to develop an entirely new vocabulary to describe what they find. Traditional biological terms often don't apply to organisms living under such extreme conditions. Take the term piezophite organisms that have adapted to high pressure. But it's not just adaptation. These creatures have evolved entirely different biological strategies. Their proteins fold backwards compared to surface proteins. Their cell membranes are inside out by our standards. They've essentially evolved a mirror image biochemistry that only works under pressure. There's hadal gigantism, the tendency for some deep trench creatures to grow much larger than their shallow water relatives. But we don't fully understand why. Is it the cold slowing their metabolism, allowing them to grow larger? Is it the lack of predators? Is it the need to range over large areas to find food? Each theory has evidence for and against it. Scientists have coined the term chemosynthetic oases to describe the areas around hydrothermal vents where life blooms in the darkness. But these aren't oases in any traditional sense. They're more like alien ecosystems that happen to exist on Earth. The food webs here are inverted, with bacteria at the base instead of plants. Energy flows upward from the Earth rather than downward from the sun. Every expedition to the Mariana Trench seems to discover something that shouldn't exist according to our current understanding. Let me share some of the most bewildering finds. In 2014, researchers discovered viruses in the Mariana Trench that are unlike anything on the surface. These viruses infect the bacteria living at extreme depths, but here's the strange part: the viruses seem to help their hosts survive. Instead of killing the bacteria, they integrate into their DNA and provide genes that help the bacteria withstand pressure. It's a form of evolution by viral infection that we're only beginning to understand. Another surprise: the discovery of multicellular organisms at depths where scientists thought only single-celled life could survive. In 2018, a team found primitive multicellular organisms resembling tiny plants at over 10,000 meters depth. They photosynthesize, but not using sunlight. They use the dim light from bioluminescence, and possibly even the infrared radiation from hydrothermal vents. It's photosynthesis in a place where photos light shouldn't exist. Then there's the mystery of the impossible currents. Classical oceanography said that water at the bottom of trenches should be still, trapped by the topography. But measurements show currents in the Mariana Trench that pulse rhythmically, almost like the trench is breathing. These currents bring nutrients and oxygen to the deepest points, creating a more dynamic environment than anyone expected. In 2020, scientists discovered that some areas of the Mariana Trench are actually warming, not from climate change. The heat is coming from below. Radioactive decay in Earth's core produces heat that seeps upward, creating warm spots on the trench floor. These thermal oases support unique communities of organisms adapted to temperatures slightly higher than the surrounding water. The true rulers of the Mariana Trench aren't the fish or the amphipods, they're the microbes. And the diversity of microbial life in the trench is staggering. Recent genetic surveys have identified over 10,000 different types of bacteria and archaea in the Mariana Trench, many of them completely new to science. Each cubic centimeter of sediment contains millions of microbial cells, each one adapted to the extreme conditions in slightly different ways. Some of these microbes are autotrophs, producing their own food from chemicals. Others are heterotrophs, consuming organic matter. Still others are something in between, mixotrophs that can switch between producing their own food and consuming others depending on conditions. It's a flexibility that doesn't exist in most surface ecosystems. The metabolic strategies of these microbes read like science fiction. Some breathe metals instead of oxygen, using iron or manganese as electron acceptors. Others produce methane as a waste product, contributing to the greenhouse gases that eventually reach the atmosphere. Some can switch between different metabolisms depending on what chemicals are available, like metabolic Swiss Army knives. One group of archaea found in the Mariana Trench appears to be among the slowest growing organisms on Earth. They divide maybe once every 100 years, possibly less, yet they're successful, numerous, and have probably existed in the deep for millions of years. They've achieved a kind of biological immortality through extreme patience. The viruses in the Mariana Trench are equally remarkable. There are more viruses in the trench than there are stars in the observable universe. They infect everything from bacteria to amphipods, moving genes between organisms, driving evolution in ways we're only beginning to appreciate. Some scientists believe that viruses might be the primary drivers of evolution in the deep sea, constantly shuffling genetic material between organisms. The chemistry happening in the Mariana Trench would make an alchemist jealous. Chemical reactions that are impossible at the surface occur naturally in the deep. Under extreme pressure, water molecules can form exotic structures called clathrates, cage-like arrangements that can trap other molecules inside. Methane clathrates in the Mariana Trench lock away vast amounts of greenhouse gases. If these deposits were ever disturbed and released, they could significantly impact global climate. The pressure also enables chemical reactions that require enormous energy at the surface. Amino acids, the building blocks of proteins, can form spontaneously under trench conditions. Some scientists speculate that the high-pressure environment of deep ocean trenches might have been crucial for the origin of life, providing the energy needed to build complex molecules from simple ingredients. Serpentinization is another remarkable process occurring in the trench. When seawater reacts with certain rocks from Earth's mantle, it produces hydrogen gas and heat. This process creates chemical energy that organisms can use, essentially turning rocks into food. It's geology feeding biology in the most direct way possible. The carbon cycle in the Mariana Trench is unlike anywhere else on Earth. Carbon from dead organisms usually returns to the atmosphere relatively quickly through decay and respiration. But in the trench, carbon gets buried in sediments and pulled into Earth's interior through subduction. This carbon might not see the surface again for millions of years, if ever. The trench is a carbon sink of planetary proportions. The pharmaceutical potential of Mariana Trench organisms is only beginning to be explored, but what we've found so far is revolutionary. A compound isolated from a deep-sea sponge shows promise as a treatment for Alzheimer's disease. It appears to prevent the formation of protein plaques that damage brain cells. The compound works in a completely novel way, different from any existing Alzheimer's treatment. Bacteria from the trench produce antibiotics that are effective against drug-resistant tuberculosis. These bacteria have been fighting each other with chemical weapons for millions of years, evolving antibiotics far more sophisticated than anything we've developed in labs. One of the most exciting discoveries is a protein from a deep-sea snail that acts as a powerful painkiller. It's thousands of times more potent than morphine but isn't addictive. The snail uses it to paralyze prey, but for humans, it could revolutionize pain management. Deep-sea organisms are also providing new tools for biotechnology. Enzymes from trench bacteria are being used to develop better laundry detergents that work in cold water. DNA polymerases from heat-loving microbes near hydrothermal vents have made possible the PCR tests used for everything from COVID-19 detection to forensic analysis. The antioxidants produced by deep-sea organisms to protect against pressure damage are being studied for anti-aging treatments. These compounds are far more powerful than vitamin C or E, and they work through mechanisms we don't fully understand. The acoustic environment of the Mariana Trench deserves more attention. It's a hidden world of sound that we're only beginning to explore. Hydrophones placed in the trench have recorded an astounding variety of sounds. There's the constant background crackling of small earthquakes, like popcorn popping in slow motion, the groans and rumbles of the Earth's crust shifting, the explosive sounds of underwater landslides that can travel thousands of kilometers, but mixed with these geological sounds are biological ones that remain mysterious. In 2016, researchers recorded what they called the Mariana Trench cry, a sound that lasted 3 seconds and covered a huge frequency range from 38 Hz to 7.5 kHz. It sounded metallic, almost synthetic, but analysis suggested it was biological. The leading theory is that it was a previously unknown type of whale call, but no one knows for sure. There are rhythmic clicking sounds that might be communication between deep-sea creatures, whistles and moans that don't match any known animal, low-frequency pulses that could be anything from geological processes to unknown organisms. The pressure at these depths changes how sound travels. Sounds can travel much farther in the deep ocean than at the surface, potentially allowing communication over vast distances. Some scientists speculate that deep-sea creatures might use sound to navigate and communicate in ways we haven't imagined. The discovery of sound-producing organs in deep-sea fish that were thought to be silent has opened up new questions. Why would fish that live in eternal darkness, under crushing pressure, evolve the ability to make sounds? What are they saying to each other in the darkness? If there were an Olympics for extreme survival, the organisms of the Mariana Trench would sweep the medals. Consider Thermococcus piezophilus, a microbe that not only survives but thrives at pressures that would crush most life. It grows fastest at 700 atmospheres of pressure. At normal surface pressure, it dies. It's so adapted to pressure that it's essentially addicted to being crushed. Or take Colwellia marinamania, a bacterium that can survive in multiple extreme conditions simultaneously: high pressure, near freezing temperature, and high salt concentration. It's like an organism training for a biological triathlon of harsh conditions. The amphipod Hirondelia gigas can survive pressure changes that would kill most organisms. It can be brought from 10,000 meters depth to 2,000 meters and survive, a pressure change equivalent to going from sea level to the vacuum of space. How its cells don't explode from decompression is still a mystery. Some organisms in the trench can survive without oxygen for extended periods, switching to alternative metabolisms. Others can withstand levels of hydrogen sulfide that would be lethal to surface life. Still others thrive in pH conditions that would dissolve most organisms. The cumulative effect of studying these extremophiles is humbling. Every time we think we've found the limits of life, organisms from the Mariana Trench push those boundaries further. The Mariana Trench isn't just important for understanding Earth, it's crucial for understanding the potential for life elsewhere in the universe. Jupiter's moon Europa has a subsurface ocean beneath its icy crust. The pressure at the bottom of Europa's ocean is estimated to be similar to that in Earth's deep trenches. If life exists on Europa, it might resemble the pressure-loving organisms of the Mariana Trench more than anything else on Earth. Saturn's moon Enceladus shoots geysers of water into space from its subsurface ocean. Analysis of these geysers reveals chemistry similar to Earth's hydrothermal vents. The lessons we're learning from chemosynthetic ecosystems in the Mariana Trench could help us understand potential life on Enceladus. Even Mars, now a frozen desert, once had oceans. If life evolved in those ancient Martian seas and retreated underground as the planet dried, it might have adapted to conditions similar to Earth's deep trenches. High pressure, no light, chemical energy sources. The study of extremophiles in the Mariana Trench has expanded the concept of the habitable zone, the region around a star where life might exist. We now know that life doesn't necessarily need to be on a planet's surface. It could exist in subsurface oceans, in deep trenches, in places we once thought were absolutely uninhabitable. The Mariana Trench has captured human imagination in ways that go beyond science. It's become a metaphor for the unexplored, the mysterious, the unreachable. In literature and film, the trench represents the ultimate frontier, the place where monsters might still lurk. From Jules Verne's 20,000 Leagues Under the Sea to modern movies like The Meg, the deep ocean has been portrayed as Earth's last hiding place for the impossible. But the real Mariana Trench is more interesting than fiction. The actual creatures living there, the transparent sea cucumbers, the giant amphipods, the snailfish with their gelatinous bodies are more alien than most science fiction creations. The trench has also become a symbol in psychology and philosophy. Deeper than the Mariana Trench has become a way to describe profound depression or deep thoughts. It represents the unconscious mind, the hidden depths of human nature, the mysteries we carry within ourselves. Indigenous Pacific cultures have long had stories about the deep ocean, about spirits and ancestors residing in the deepest waters. These stories, passed down through generations, often contain surprisingly accurate observations about deep-sea phenomena, suggesting that traditional knowledge recognized the importance of the deep ocean long before modern science. The Mariana Trench faces an uncertain future. Despite its depth and isolation, it's not immune to human impact. Deep-sea mining companies have identified the trench and surrounding areas as potential sources of rare minerals. Manganese nodules, which take millions of years to form, could be harvested for electronics manufacturing. The impact on deep-sea ecosystems would be devastating and likely irreversible. Climate change is altering the chemistry of the deep ocean. As the surface ocean absorbs more CO2 from the atmosphere, it becomes more acidic. This acidification eventually reaches the deep ocean, affecting the shells and skeletons of deep-sea organisms. Some scientists predict that within a century, the water in the Mariana Trench could become too acidic for many current inhabitants to survive. Noise pollution from shipping, military sonar, and industrial activities is penetrating the deep ocean. The Mariana Trench, once one of the quietest places on Earth, now regularly experiences human-generated noise. This could disrupt the behavior of deep-sea organisms that rely on sound for communication and navigation. Plastic pollution continues to accumulate. Every piece of plastic that enters the ocean has the potential to eventually sink to the deepest points. The organisms that have evolved over millions of years to efficiently extract nutrients from marine snow are now also efficiently extracting microplastics, incorporating human waste into their bodies at the cellular level. Yet there's hope. The Mariana Trench's designation as a U.S. national monument provides some protection. International efforts to create marine protected areas in the deep ocean are gaining momentum. New technologies for removing plastic from the ocean are being developed, though none yet work at extreme depths. The next decade promises to revolutionize our understanding of the Mariana Trench. Autonomous underwater vehicles, AUVs that can operate for months at a time, are being developed. These robot explorers will map the trench in unprecedented detail, discovering features and organisms that human-piloted vehicles might miss. Environmental DNA, eDNA, sampling is allowing scientists to detect organisms without seeing them. By analyzing water samples for genetic material, researchers can identify what lives in an area without disturbing the ecosystem. This technique has already revealed that the diversity of life in the trench is far greater than visual surveys suggested. Artificial intelligence is being trained to identify new species from video footage, to predict where valuable discoveries might be made, and to control robotic vehicles in real time. Machine learning algorithms can process the vast amounts of data from deep-sea expeditions, finding patterns that human researchers might miss. New materials are making deeper, longer expeditions possible. Metallic glasses that are stronger than steel, but more flexible. Ceramics that maintain their strength under extreme pressure. Bio-inspired materials that mimic the pressure-resistant properties of deep-sea organisms. But perhaps the most exciting development is the democratization of deep-sea exploration. Advances in technology are making it possible for smaller countries and institutions to build deep-sea vehicles. The secrets of the Mariana Trench won't be unlocked by a few wealthy nations, but by a global community of explorers. The Mariana Trench challenges our most basic assumptions about life, Earth, and our place in the universe. It shows us that life doesn't need what we think it needs. Not sunlight, not moderate pressure, not comfortable temperatures. Life needs only energy, in whatever form it can find, and the chemical building blocks to construct itself. Everything else is negotiable. The trench reminds us that we are surface creatures with a surface perspective. We've organized our entire understanding of biology around the thin film of life that exists in the zone we inhabit. But that zone represents less than 1% of Earth's biosphere by volume. The vast majority of our planet's living space is in the deep ocean, in conditions we consider extreme but which are actually the norm for Earth. It also raises profound questions about consciousness and intelligence. If organisms in the Mariana Trench have evolved complex behaviors, communication systems, and problem-solving abilities, do they have some form of consciousness? Are we alone in our self-awareness, or does consciousness emerge wherever information processing becomes sufficiently complex? The isolation of deep-sea organisms raises questions about evolution and progress. These creatures have been evolving for millions of years, possibly longer than life has existed on land, yet they haven't developed technology or civilization as we understand it. Does this mean that intelligence and technology are unlikely evolutionary outcomes, or simply that they're only possible in certain environments? The Mariana Trench has inspired artists and creators in unexpected ways. Musicians have composed symphonies based on the sounds recorded in the trench. The composer Lily Chen created Challenger Deep, a piece that uses actual hydrophone recordings from the trench, mixed with orchestral instruments played at extremely low frequencies. The result is music that seems to come from another world, beautiful and alien simultaneously. Visual artists have been inspired by the bizarre forms of deep-sea life. The bioluminescent displays of deep-sea creatures have influenced everything from fashion design to architecture. The Tokyo architect Yamamoto designed a building with a facade that mimics the light-producing cells of deep-sea jellyfish, creating a structure that seems to glow from within. Writers have found in the Mariana Trench a perfect metaphor for the human condition, the pressure we all feel, the darkness we navigate, the strange beauty we create in impossible circumstances. The poet Maria Santos wrote, "We are all creatures of the trench, adapted to our own impossible pressures, glowing with our own strange light, in the darkness we've learned to call home." The Mariana Trench represents enormous economic potential, an enormous economic risk. The organisms of the trench could be worth trillions of dollars in biotechnology applications. A single enzyme that works under extreme conditions could revolutionize industrial processes. A new antibiotic could save millions of lives. A novel compound could lead to breakthroughs in materials science. But the cost of accessing these resources is staggering. A single expedition to Challenger Deep costs millions of dollars. Developing a new deep-sea vehicle can cost hundreds of millions. The infrastructure needed to support regular deep-sea research, ships, ports, laboratories, requires billions in investment. There's also the question of ownership. Who owns the organisms of the Mariana Trench? The countries whose waters they inhabit, the companies that discover them, all of humanity. International law is still catching up to the realities of deep-sea exploration. The potential for deep-sea mining adds another economic dimension. The minerals in and around ocean trenches could be worth hundreds of billions of dollars. But the cost of extracting them, both financial and environmental, might exceed their value. Exploring and understanding the Mariana Trench is not a project for a single generation. It's a multi-generational mission that will require sustained effort over centuries. We are perhaps in the position of early Antarctic explorers, making the first tentative journeys into an unknown realm. Future generations will look back at our primitive submersibles and limited understanding the way we look back at the wooden ships and canvas tents of polar explorers. Young people entering marine science today will spend their entire careers studying organisms and processes we haven't even discovered yet. The children being born now might be the first generation to see comprehensive maps of the entire ocean floor, to understand the full diversity of deep-sea life, to unlock the medical and technological secrets of the abyss. This generational perspective is important because it puts our current efforts in context. Every sample collected, every species discovered, every measurement taken is not just data, it's a legacy we're leaving for future scientists. Pacific Islander cultures have known about the deep ocean for thousands of years, encoding knowledge about currents, depths, and marine life in stories, songs, and navigation techniques. The Chamorro people of the Mariana Islands have legends about Pontan and Fuuna, primal beings whose bodies became the earth and sky. In some versions of the story, the deepest parts of the ocean are where Pontan's heart still beats, sending pulses through the water, a poetic description of the geological activity in the trench. Traditional navigators from various Pacific cultures could detect deep ocean features by watching wave patterns, bird behavior, and even the color of clouds reflected from the water. They knew where the deep places were, even if they couldn't visit them. This traditional knowledge is now being combined with modern science in powerful ways. Indigenous knowledge holders are working with marine scientists to identify important areas for protection, to understand long-term changes in ocean conditions, and to develop sustainable practices for ocean use. Why should someone living far from the ocean, perhaps in a landlocked country, care about the Mariana Trench? Because the trench is part of the system that makes Earth habitable. The deep ocean absorbs heat and CO2 from the atmosphere, moderating global climate. It cycles nutrients that eventually support fisheries feeding billions of people. It generates oxygen through photosynthetic organisms in the upper waters, influenced by nutrients brought up from the deep. Because the organisms of the trench might save your life one day. The antibiotics, anti-cancer drugs, and other medicines being developed from deep-sea organisms could benefit anyone, anywhere. Because the trench represents hope. If life can thrive under 16,000 pounds per square inch of pressure, in eternal darkness, in near-freezing water, then life might exist anywhere in the universe. We are not alone, even if our companions are microbes in the mud of alien worlds. Because the trench reminds us that Earth still holds mysteries. In an age where it can feel like everything has been explored, commercialized, and Instagram posted, the Mariana Trench remains largely unknown. It's proof that there are still frontiers, still discoveries to be made, still wonders to uncover. As we near the end of our journey into the Mariana Trench, let's consider the ultimate questions this place raises. What is life? The organisms of the trench have expanded our definition so far that we must ask whether we even understand what life is. If life can exist under these conditions, what other forms might it take that we haven't imagined? What are the limits of adaptation? Every organism in the trench has pushed against the boundaries of what's possible, adapting to conditions that would instantly kill their ancestors. How far can evolution push life? Are there conditions that are truly incompatible with life, or is life infinitely adaptable? What is our responsibility to places we've never seen? Most people will never visit the Mariana Trench, never see its creatures except in documentaries, yet our actions affect it. What obligation do we have to protect places that exist beyond our direct experience? How do we balance knowledge and preservation? Every expedition to the trench risks damaging what it studies. How do we learn about these environments without destroying them? How much knowledge is worth how much impact? What does the trench teach us about ourselves? We are products of evolution, shaped by the same forces that created the organisms of the deep. What does their existence say about the nature of life, consciousness, and our place in the universe? As our exploration comes to an end, let's take one final imaginary journey to the bottom of the Mariana Trench. You're in a submersible, descending through the water column. The sunlight fades within the first few hundred meters. By 1,000 meters, you're in eternal darkness except for your lights and the occasional flash of bioluminescence. At 4,000 meters, you've entered the abyssal zone. The pressure is 400 times what you experience at the surface. The water temperature is just above freezing, yet life surrounds you. Jellyfish drifting like ghosts, squid with eyes the size of dinner plates, fish with mouths full of needle teeth. At 6,000 meters, you're deeper than most of the ocean floor. The pressure would crush a human body in milliseconds, yet amphipods swim past your window, seemingly unaffected by the weight of water above. At 8,000 meters, you've entered the Haddle Zone, the realm of the trenches. Few humans have been this deep. The pressure is over 800 atmospheres. Your submersible creaks and groans, but holds. At 10,000 meters, you're approaching the deepest point on Earth. The seafloor comes into view, a lunar landscape of sediment and rocks, but it's not barren. Bacteria coat every surface. Sea cucumbers leave trails in the mud. Amphipods scurry through the sediment. Finally, at 10,994 meters, you touch down at Challenger Deep. You are now at the deepest known point in Earth's ocean, under more pressure than exists anywhere else on the planet's surface. Outside your small sphere of light, the darkness is absolute, the silence is profound, but you're not alone. Life is here, has always been here, will always be here. In this place that seems impossibly hostile to life, life thrives. It's a reminder that our planet is more resilient, more creative, more wonderful than we often realize. As we ascend from the depths of our imagination, rising back to the world of air and sunlight, let's carry with us the lessons of the Mariana Trench. Life is more adaptable than we ever imagined. The organisms of the trench have shown us that life can exist almost anywhere, under almost any conditions. This gives us hope for Earth's resilience, for the possibility of life elsewhere in the universe, for our own ability to adapt to changing conditions. The unknown is not empty. The parts of our world we haven't explored aren't blank spaces. They're full of wonders we haven't discovered yet. Every mystery solved reveals new mysteries. Every answer raises new questions. We are connected to places we'll never see. The Mariana Trench affects global climate, ocean chemistry, and the evolution of life on Earth. We are connected to its creatures through our shared biochemistry, our evolutionary history, and our planet's interconnected systems. Pressure creates diamonds, and unique life. The extreme conditions of the trench haven't prevented life. They've created unique forms of it. Sometimes the most beautiful, remarkable, and valuable things come from the most challenging conditions. There are always deeper depths. No matter how far we've explored, how much we think we know, there's always more to discover. The Mariana Trench reminds us to stay curious, stay humble, and keep exploring. And now, dear listener, as you drift towards sleep, perhaps you can imagine the gentle rhythm of the deep ocean, not the crashing waves of the surface, but the slow pulse of the abyss. Imagine the marine snow, falling constantly through the darkness like an upside-down snowstorm, each flake a tiny packet of nutrients, drifting toward the bottom. It's been falling for millions of years, and will continue for millions more. Imagine the creatures of the deep, moving through their dark world with perfect confidence. They don't know they live in an extreme environment. To them, it's simply home. They navigate by touch, by chemical signals, by sounds we can't hear, by senses we don't possess. Imagine the water itself, ancient and patient, circulating through the global ocean system on a journey that takes centuries. The water at the bottom of the Mariana Trench today was at the surface when Vikings sailed the North Atlantic. It will return to the surface when our great-great-great-grandchildren are old. Imagine the pressure, not as something crushing, but as something embracing. The organisms of the trench are held by the ocean, supported by it, shaped by it. They exist in a state of perfect equilibrium with their environment, neither fighting against it, nor surrendering to it, but living in harmony with it. As you sink into sleep, know that beneath the world's oceans, in places darker than space, and under pressure that defies comprehension, life continues its ancient dance. Bacteria divide, amphipods feed, fish swim through the darkness, the earth's crust shifts and groans, chemical reactions proceed, evolution continues its patient work. The Mariana Trench doesn't sleep, it doesn't rest, it simply continues, as it has for millions of years, as it will for millions more. A place of pressure and darkness, yes, but also a place of life and wonder, a reminder that our planet still holds secrets, still offers mysteries, still has stories to tell, sweet dreams. And remember, at this very moment, 11 kilometers below the Pacific waves, in the deepest place on Earth, life goes on. Strange, beautiful, impossible life, thriving in the darkness, proving once again that our world is more remarkable than we can imagine. The deep calls to the deep, and life answers, always.